Hi everyone, welcome back to my classes. We are going to see some more concepts on probability. Let us start. Sample space. Sample space means what? If you consider some experiment, if you conduct some experiment, what are all the possible outcomes? For example, if you toss a coin, one coin, then the sample space will be, what are all the possibilities? H and T. Okay, H and T. Similarly, if you toss two coins, then what are all the possibilities? In the first coin you may get head, in the second coin also you may get a head. In the first you can get a head and second tail, or tail and head, and both can be tails. So these are all the possible outcomes. So what are all the possible outcomes? They will constitute the sample space. You put everything in the set, that is the sample space. Okay, and if they are not finite, if they are finite, we'll write like this in the set. If it is not finite, then it will be written in the statement or rule form of the set, right? So like this, X is a city with a population over 1 million. That means how many cities are, you cannot write all the cities in a set form like this, right? It will be, there are infinite number of sample points. So we cannot write all the cities with over 1 million, okay? Population over 1 million. Therefore, you write it in the set form, statement form of the set. Next one, suppose if you consider x squared plus y squared is equal to 4. We know that it is a circle of a radius. It is a circle of radius 2 and center origin 0, 0, right? And now we have less than or equal to. Less than or equal to means inside the circle. Therefore, S is the set of all points x comma y on the boundary or interior of the circle of radius 2 and center at the origin. Okay. So now, event means it is a subset. That means you know the sample space is this one. And event means which satisfies some condition. Subset of S which satisfies some condition. Suppose if you consider event A which satisfies the condition divisible by 3, then the outcomes will be A is equal to 3, 6, which is a subset of S. In this case, we can call A as an event. Okay. Trial means what? If you consider some experiment, for example, if you conduct some experiment in the physics lab, I'll give you one small example. Physics lab, I want to measure the length of one wooden piece. Okay, so if you want to consider the length, if you want to find out the length, what will you do? You will put it in the vernier calipers and find out the length. What will be the outcome? Only one particular value, right? Only one value will be the outcome. Can you say that sometimes for the same wooden piece, can you get two different measures? Not possible at all. Only one is possible, right? Therefore, it is ordinary experiment. It is not statistical experiment. When you get one of the more than one of these outcomes, then it is called a trial. In the statistical probabilistic experiment, you will get the outcomes will be more than one. Then we call it as a trial. Okay, so tossing a coin is a trial, and getting a head and getting a tail is an event. See, I am conducting the experiment of tossing a coin, and the outcome will be a head or a tail. Getting one head, sample space S is equal to set of all H comma T. But if you get a head alone, if you consider this alone, it is an event. If you consider tail alone, it is an event. Understood? Similarly, throwing a die is a trial, and getting 1 or 2 or 3 or 4 or 5 or 6, okay, is an event. Getting 1 is an event. Getting 2 is an event. Similarly, up to getting a 6 is also an event, right? Next is complement. Complement of an event with respect to S. Already you would have studied in your set theory this. The same thing is applicable here also. Suppose here in the place of universe set, we will consider the sample space. For example, if you throw a die, the outcomes are 1, 2, 3, 4, 5 and 6. This is the sample space, right? Suppose A is an even number. Okay, so then 2, 4, 6. then what will be in A bar, complement of A? It will not be an even number. The condition will be if A is a set that A is an even number, the outcome is an even number. A bar will be, it is not an even number. So remaining are 1, 3, 5. Okay. And if you take A union A bar, that should constitute the sample space. Yes. Okay. And intersection. And what will be the intersection here? A and A bar will be empty. Intersection means there are some common elements. Suppose A is a set I am considering divisible by 3. And B is an event I am considering divisible by 2. Outcome should be divisible by 2. What will be A then? A will be the set 3, 6 divisible by 3. And B is the set divisible by 2. So 2, 4, 6. Right? What will be A intersection B? The common elements 6. That means it should be divisible by both 2 and divisible by 3. That is, it should be both in A and B. Okay. So A intersection B will be the common element 6. Suppose if you want to find out A union B here, then here 3, 6, 2, 6. Every element should be written. Either it can be either in A or in B or both. Okay. And 2, 3, 4, 6 will be the answer of A union B. We don't write 6 twice. Okay. Any element for the set, we are not supposed to write repeatedly. 6 is twice also, you write only once. Okay. Union. Now, we have some techniques, that is countings of sample points. All these things we have studied in your intermediate itself. This is just a revision. Okay. So, multiplication rule already you have studied. If an operation can be performed in n1 different ways, and for each one of these a second operation can be performed in n2 different ways, then the two operations can be performed together in n1 into n2 ways. Example, I'll tell you. If you if you throw 2 dice, let us take two dice. First die can be, or how many sample points are there in the sample space when a pair of dice is thrown? Now consider a pair of dice. So first die is there, second die is also there. Okay, only once we are throwing. So first die you will get 6 possible ways. What are the possibilities? 1, 2, 3, 4 and 5 and 6. These are the possibilities in the first die, right? In the first one, if first is 1, for this one, from the second die you can have 1, 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6. That is, for 1 we get all the 6. Similarly, for 2 also we will get all the 6 and so on. Here 6, 1 is possible. Last is 6, 6. In the previous video you would have observed. In the live class we have discussed this, no? 6 times here, and second is also 6 times. Means 6 into 6. That is, for each 6 you will get all the 6. For 1 you get all the 6. For 2 you get all the 6. And so on. So there are 36 ways. Right? This is an extension of the previous formula. If an operation can be performed in n1 ways, and next for each of the first one, second operation can be performed in n2 ways and so on. Then number of sequence of k operations can be performed in n1 into n2 into etc. up to nk ways. Right? We'll see some examples. Sam is going to assemble a computer by himself. He has the choice of considering the chips from 2 brands. That means N1 is equal to 2. Let us take N1 as the chip. And N2, a hard drive from 4 brands. So N2 is 4. And memory from 3. So N3 is equal to 3. And accessory bundle N4 is equal to 5. So how many different ways can Sam order the parts? So first you can take 2. And for each one you can take 4 from the hard drives, and similarly for each of these combination you can take 3 ways. The memory can be selected in 3 ways, and accessory from accessory bundles you can take 5 ways, right? Therefore, it is 120 ways. So, Sam can order the parts in 120 ways. I hope you understood. Next. Next, there is a definition for partitioning of set. If you have n objects and there are R cells, these n objects can be put in R cells in such that n1 in the first cell, n2 in the second cell, and etc. nr in the rth cell. Then how many ways they can be put? NC, this is like NCR only. Okay, so NC in the place of R, you have N1, N2, etc. NR. This is the definition. This is n factorial divided by N1 factorial into N2 factorial into etc. NR factorial, where this sum is N. This is important. This M should be N. Okay, the total should be N. Sorry. In how many ways can 7 people be assigned to 1 triple and 2 double hotel rooms? So there are 7 people. We have, that is n people can be accommodated in one. We have 1 triple bedroom and we have 2 bedrooms, double bedrooms. Okay, so 1 triple room and 2 double rooms. 7 people have to be accommodated in this. How many ways? 7, and we have 3. So 3, 2, 2. Okay. So 7 factorial divided by 3 factorial into 2 factorial into 2 factorial ways. That is 7 factorial is 7, 6, 5, 4, 3, 2, 1 divided by 3 factorial is 3 into 2 into 2 into 2. So 1, 2 will get cancelled. 4, 2, 2, 3, 3. So 210 ways. Understood? Next is equally likely events. See, the definition you can see, the reason of there will not be, suppose if you have consideration of outcomes, if you consider the outcomes, no outcome will have any preference over the others. That is, the meaning is, if you toss a coin, we have getting a head 1. The probability of getting a head is there, probability of getting a tail. These two will be equal. Okay, see here, this is both are 1 by 2. This is also 1 by 2, this is also 1 by 2. Similarly, if you throw a die, you will get the numbers 1, 2, 3, 4, 5, 6. For probability, if you consider, what is probability of 1? 1 by 6. Here 1 by 6. All are equal. You cannot say that I like the number 5. I will get, my lucky number is 5. So, I will get this for 2 times. No, never. This will also happen only once only. Okay. So, 1 by equally likely. All the outcomes, probability of all the outcomes will be distributed equally. Then only we say that equally likely events. Okay. Next is mutually exclusive events. Say for example, if you toss a coin, when you are tossing a coin, you may get a head or you may get a tail. At the time of getting head, is it possible if you toss a coin, when you are getting a head, this is one event, this is another event, right? When you are tossing a coin, if you are getting a head, is it possible to get the tail also simultaneously? Never. If you get a head, tail will not come at all, right? So similarly, if you get a tail, you cannot get head at all. Okay, head is not possible, only tail will come. Only one will come at a time. That is why the occurrence of an event excludes the occurrence of the other event. Understood? So all these definitions are very, very important, right? Mutually exclusive. These two are mutually exclusive. Similarly, if you throw a die also, if you get one number, only one number is possible at a time. If you are getting 2, all the other 5 are mutually exclusive to this particular event, and so on. Okay. And independent events. Say several events are said to be independent if the happening of an event is not affected by the occurrence of any number of remaining events. Listen, now you will get a little confusion between independent and mutually exclusive. Mutually exclusive means if one event is occurred, the other events cannot occur. That is mutually exclusive. Independent means, I'll give you one example. I'll explain, you will understand clearly. I have two coins, coin 1 and coin 2. And one after the other I'm tossing this first coin. I am getting head. Okay. For example, second coin I am throwing now. I am tossing the second coin now. I am getting a tail. Can you say that because I got the head in the first one, I have to get the tail in the second coin? Is it possible? Can you say like this? No, it is not like that. It does not depend. Is this event depend on the first one? No, it is not depending on the first one. So these two are independent. Otherwise, if I get head in the first one, second also I'll get head. Can you say like that? Because of this event, this did not happen. Okay. This need not, the second event need not happen because of the first one. It does not depend on this. So these are independent events. These two are independent events. Okay. In the next live class, you come up with some dependent events. I'll give you one problem in the next live class. But you also think, okay, dependent events. You give some example for dependent events. Okay. Now, in tossing a coin, event of, that's what I have explained. In the tossing of coin, the event of getting a head in the first toss is independent of getting a head in the second, third and subsequent throws. Okay. Next is exhaustive events. That is the total number of possible outcomes. That is whatever we are writing in the denominator in probability. That is exhaustive event. That is also called exhaustive events. In tossing a coin, there are two exhaustive events. One is head and tail. Okay. Similarly, if you have cards, then in drawing two cards from a pack of cards, the exhaustive number of cases is 52C2. There are totally 52 cards. In the live class, and in the next live class, I'll explain these cards also. Okay. So 52C2 is, because we are having 52 cards, we are taking two cards. So 52C2 is the exhaustive number of, that is total number of possible ways. We have written in the denominator, no, that same thing. It is 52C2. Now we have beautiful definitions for probability. There are three different probabilities. Okay. First one is the classical probability. Probability, we know there are three different, there are definitions of probability, and according to the requirement, depending on the problem, we have to take the definition according to our requirement. Okay. Let us see, first one is classical probability. This rests on an important assumption that all basic outcomes are equally likely. This is important. Okay. This is assuming, we are assuming here that all the outcomes are equally likely. Only for those kind of problems we can use this. Okay. So probability of an event is number of basic outcomes that satisfy the event A divided by total number of outcomes in the sample space. Okay. This is the condition. But this condition of equally likely is often not satisfied. This condition, what is the condition? It should be equally likely. All the outcomes should be equally likely. This is the assumption we are taking. With this assumption only we are defining this probability. Okay. So this condition of basic outcomes should be equally likely is often not satisfied. Sometimes we talk about the, when we talk about the real world applications, it will not be useful. Okay. That is why we need more definitions, right? So we are considering the empirical probability. When will you see this empirical probability? If you have data and you can derive the proportions from the historical data, that is previous data. The same experiments were conducted already and we have their data, and using that historical data, that's why that is when we have to use this empirical probability. Okay, and it is also called relative frequency probability. Now, the number of times the event A occurs in repeated trials divided by total number of trials in a random experiment. Okay, for example, for this empirical probability, I may look at the weather on a particular day for the last 20 years, and I say, can I use the some average of these things to make a prediction? Prediction means what? In the same day, last 20 years, what happened on a particular day? This is the average temperature. So using that, I will find out the average and I'll try to predict the weather of today. Whether it will rain or not, or it will be sunny today. Like that we can predict. Okay, that is, we are using the previous data. Or if I think of stock prices in the stock market, people in finance love to look at the last 250 days, approximately 250 trading days, and they can say how many days did the stock go up or how many days did it go down. Okay, so to find out, depending on that, we can take a decision, and based on those results, we will get empirical definitions. Okay, so number of times the event occurs in repeated trials divided by total number of trials in a random experiment. Okay, so that is also called proportion of times an event occurs in a large number of trials. We are not able to find out the number, then we can go for large. If the denominator is large, then we'll go for that infinite number and all. We have seen the same thing here. So this is used in medicine also. In the pharmaceutical industry, whenever we do drug testing, I told you already, I have explained in the introduction of COSM. Now we are trying to find out the vaccine for COVID-19, right? Now what they are doing, they'll take a sample and they will conduct the random experiments, how much it is successful. Depending on that, they'll try to find the medicine. Okay, whether the medicine is working or not, they'll find out. Now, sometimes even things get even worse. You will not have any data at all, or you will not have any clue. At that point, we go to the subjective probability definition. For example, if you want to launch a new product, already the product was not available at all. Okay, so we are trying to find out a new product. For example, if you develop some software, this kind of software is not at all developed till now. So what will be your assumption? Okay, you are thinking that you have a gut feeling that this will be 75% people will be using this, or 90% people will be using like this. You can assume this is called the subjective probability. Or sometimes depending on your experience also, depending on the product or depending on your experience, you will get a gut feeling that we can launch, we can do this, we will be successful, and so on. Okay, this is called the subjective probability. And we have some important axioms for this probability. Probability of A is the probability function defined on a field B of events if the following properties or axioms hold. Actually, for each one, these three are the axioms which are very, very important. Probability of A is defined. A is a subset of B. A is an element of B, and this should be real value. And probability of any event should be always greater than or equal to 0, and it should be less than or equal to 1. That is also important. This is very, very important. Probability value cannot be less than 0. Probability value cannot be more than 1. So this you can take it as a clue when you are doing problem. If you are asked to find out some probability of some event A, okay, if you are getting that 2.3, that means you can take it as a clue. You can take it as a tips that we have made a mistake in this problem. Okay, if you are getting the probability as more than one value or negative, then there is something wrong. Probability cannot be less than or equal to 0. It cannot be more than or equal to 1. Okay, and I think you know what is that 0 means. What? 0 means it cannot happen. Suppose if you are taking probability of A is equal to 0, then it is no, it cannot happen at all. And if you are getting probability of A is equal to 1, then it is certain event. It is called certain event. This is called impossible event. If the probability is 0, it is called impossible event. If the probability is 1, that is it will definitely happen. That is certain event. Okay. So probability of 0 means impossible. Probability of 1 means certain event. Right. So similarly, next one, that is what? Probability of, and if you take the probability of sample space, probability of sample space is always 1 because we are considering all the possible, no? So either this or that, if you consider the total probability is always 1. This is going to be useful in your random variable topics. Okay. So probability of total probability is always 1 only. That's called certainty. Now, if an is any finite or infinite sequence of disjoint events, here this is important, disjoint events in B, then probability of union, because A means sets, so you are taking unions. Then if you take all the unions and then its probability, that will be equal to the summation of each probability. Okay, this is called union or additivity rule, right? All these 3 axioms will hold for any probability. If you consider, if they are not satisfying, that means it is not a probability at all. That function will not be a probability function. Okay. And that's all for this. And in the next live class, I'll give you problems, many problems, important problems using this. Okay. And I'll let you know the live classes. The next live classes will have the problems depending on these things. Thank you. Thank you so much for listening. Take care. Stay safe.